I now call to order the Society's 2,498th meeting in what is now the 153rd year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's PSW meeting and the lecture by Mike Griffin. The Society is grateful to PSW Full Year Series sponsors, PSW member Mike Helton, and Helton Associates LLC for their support. Thank you, Mike. We are also grateful to PSW members AJ Kathari and Ravi Deepak for sponsoring tonight's lecture, and to AJ in particular for bringing Mike to us. Thank you, AJ. I am pleased to announce the following new members have been admitted to the Society, and there are quite a few, so bear with me. Victor Golitsky, professor of physics at the University of Maryland, interested in quantum physics, quantum information theory, materials physics, and quantum computing, who learned at PSW from PSW member Robert Thompson. Thank you, Robert. Will Deacon, a physicist with Lightcast Discovery, interested in physics, electronics, nanotechnology, and biotechnology, who earned a PSW from PSW member Connor Nixon. Both of them are here. Welcome, Will, and thank you, Connor. Will Brazelton, captain retired, American Airlines, interested in astronomical engineering, spacecraft design, rocket propulsion, and orbital mechanics, who learned a PSW from a PSW member. Paul Cote, professor at the University of District of Columbia, interested in a wide range of subjects, including AI, ML, cybersecurity, game theory, numerical analysis, and biomedical applications of statistics, who learned a PSW through the Washington Academy of Sciences. Jeff Hughes, an electrical engineer employed by the U.S. government, interested in AI, ML, autonomy, and electromagnetic operations, who earned a PSW from PSW member Cameo Lance. I think Jeff and Cameo are both here, so welcome, Jeff. Thank you, Cameo. Robert Higgins, a U.S. Army medic and a student at Penn State majoring in biobehavioral health, interested in infectious disease research, who earned a PSW from a social media post. And Stephen Reinhardt, an astrophysicist at NASA, interested in physics, astronomy, planetary science, neuro and cognitive science, among other topics, who earned a PSW from being A+1 at a PSW dinner. And tonight's speaker, Mike Griffin, learned a PSW from our invitation to him to speak here tonight, and whose interest will be clear, at least in some part, from tonight's lecture. If you are interested in membership, you can access a membership application on the PSW website by clicking on the Join button at the upper left-hand corner of the home page on our website, www.pswscience.org. And if you're here in the Powell Auditorium, you can access the application using the QR code on the business cards on the tables at the back of the room. All with a genuine interest in science are welcome to join. All members of PSW are entitled to a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington, and if they so choose, to purchase a ribbon and to wear the ribbon of the Society. If you've not received your signed copy of the bulletin, if you're a new member, please come to see me after the meeting. Recording Secretary Scott Matthews will now present the minutes of the 2,497th meeting and the presentation on the state of the Society by corresponding secretary and Executive Director, in fact, Robin Taylor and President Larry Milstein, and the discussion among those gathered thereafter about ALMI and LLMs. Scott, stage is yours.
Thank you, Larry. Good evening. On May 31st, 2024, in the members' dining room of the Cosmos Club in Washington, D.C., President Larry Milstein called the 2,497th meeting of the Society to order at 7:39 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support. Scott Matthews then read the minutes of the previous meeting, which included the lecture by Brent Seals titled Unlost, Recovering of the Texts of Burnt and Carbonized Scrolls. The minutes were approved as read, pending a minor correction. President Milstein then introduced Robin Taylor, the Executive Director and corresponding Secretary of the Society. Robin began by presenting the formal statements of the Society's mission and its, quote, program services, as detailed in the Society's tax filings. Organization's mission: an educational, scientific, and professional society organized in 1871 by Joseph Henry, the first Secretary of the Smithsonian, providing scientific lectures, education, and discussion to its members and to the public for the promotion of science, the advancement of learning, and the free exchange of views among its members and attendees on scientific subjects. Lectures and accompanying discussions are recorded and made available to all free of charge on the Society's video channels. Program Service 1. In essence, this statement says, the Society organizes and hosts 16 to 20 scientific lectures each year, and that these lectures are free of charge and open to all. It goes on to state that PSW lectures are multidisciplinary and cover all areas of science. This statement describes the pre-lecture dinner and the post-lecture social hour as an opportunity for interaction with the speakers as well as other attendees. Program Service 2. This statement details the Society's educational outreach efforts. It discusses the fact that all PSW lectures are live streamed over the internet and posted to the YouTube and Vimeo channels. It emphasizes the fact that these videos, which are viewed hundreds of thousands of times each year, are provided free of charge to viewers throughout the world. Taylor then presented the median dinner attendance and median lecture attendance over the past 10 years, broken down by academic year. The summary was that dinner attendance numbers have remained stable in spite of the pandemic, and that lecture attendance is slowly rebounding. Detailed numbers of lecture attendance and live stream viewing was presented for the past 2 years, showing the numbers for each lecture. While these numbers showed a positive trend with an increase in both in-person and online attendance, the numbers remained smaller than the pre-pandemic values. Financial data was presented, showing a year-by-year breakdown of revenue, operations expenses, investments, etc. This data showed that while the Society's income has increased year after year, the expenses have also increased dramatically. The net result is that the Society appears to be in good financial shape at present, but that additional sponsorship would help guarantee future lectures. The President's Forum was followed by a discussion session. The topic of this discussion was artificial intelligence, or AI. Several members described their personal experiences using AI, including ChatGPT, Watson X, and Copilot. Several members reported positive results, finding the reports generated by AI to be extremely helpful. Several members recounted difficulties with AI responses, essentially boiling down to the, quote, garbage in, garbage out problem. One member asked if an AI could become a member of the Society and whether she would have to pay dues. The member promptly opened an AI on his cell phone and asked her if she would like to join the Society. She declined. Several members raised concerns about the safety of AI and the degree of oversight and regulation. While some members emphasized the need for such oversight, other members expressed the idea that, quote, the cat is already out of the bag, end quote. The general consensus expressed by the members involved in the discussion seemed to be that AI and large language models can be an extremely helpful tool, but they still require the judgment of a human being to evaluate their results. After the discussion period, President Milstein thanked the attendees for their participation, announced speakers for upcoming lectures, and made a number of housekeeping announcements. He adjourned the 2,497th meeting of the Society at 9:41 p.m. Eastern Time. Temperature in Washington, D.C., 12.8 degrees Celsius. Weather, mostly cloudy. Audience in the members' dining room, 23. Respectfully submitted, Scott Matthews, Recording Secretary.
Thank you, Scott. Are there any comments or corrections or additions to the minutes? I have a couple, but I don't want to go over them here, mostly on the financial part, so I'll do that later. I did want to mention that as far as outreach goes, it's nice to note that views on our YouTube channel have now gone over 1 million. So it's pretty good for a science channel. And with that, we'll turn to tonight's lecture by Michael Griffin on returning humans to the moon, how the United States can actually get there instead of watching China do it. Mike is the co-founder and co-president of the senior level consulting services firm, and I apologize for not asking you if it's LogiQ or LogiQ. LogiQ, spelled with a Q. Previously, he was Undersecretary of Defense for Research and Engineering, served as NASA administrator, was head of the Space Department at Johns Hopkins APL, and was Executive Vice President and General Manager of Orbital ATK's Space Systems Group. He is a member of the National Academy of Engineering, the International Academy of Astronautics, an honorary fellow of the American Institute of Aeronautics and Astronautics, a fellow of the American Astronomical Society, and a fellow of the Institute of Electrical and Electronic Engineers, among many other awards, which included being one of the 100 most influential people in the world, as determined by Time magazine. It would take a long time to read through all of Mike's accomplishments, and I'm not going to do that. As he sits here nodding his head, no, no, no. Mike has earned 7 degrees, including a BA in physics from the Johns Hopkins University, a PhD in aerospace engineering at the University of Maryland, and an MBA at Loyola University, Maryland. He is also, in addition to all of that, a certified flight instructor with instrument and multi-engine ratings. And without further ado or further embarrassment, I will turn the podium over to Mike.
Thank you, Larry, and thanks for registering for this discussion. I'm looking forward to doing it and hope it will prove worthy of your time. So first of all, a little bit of a change, actually quite a lot of a change. You'll note that there are 2 authors of this because my business partner in LogiQ, our consulting practice, is Dr. Lisa Porter. I could embarrass her by reciting her accomplishments, but then I have to work with her afterwards, so I won't. But it started out that I was asking her to review what I was doing, and so many improvements were made, and they weren't just changes; they were improvements, and I had to see that they were. So I reached the point where I said, it's just not fair for me to do this unless you agree to be a co-author. It took some persuading, and usually I don't win, but after a little while, I wore her down, and she agreed to accept a co-authorship. So Lisa, if you would just quickly wave to people. Stand up. So I also have to say that, as AJ knows, who was the person who asked me to do this, this lecture is based on congressional testimony that I provided back in January at the request of the House Science Committee. And that testimony was enormously shaped also by Lisa. So this whole thing just wouldn't exist without her, and I would be remiss if I didn't acknowledge that. So, thank you. when Larry asked me for an abstract and all that, I had not gotten nearly so far with this, so I didn't have the right title page and didn't have the right authorship, and I wanted to correct the record. So there were other people who helped a lot as well. Colleagues from my NASA and APL Space Department days, Doug Cook and Walt Falconer, who worked over the architectural and system engineering and math features, the only thing I'm qualified to do in this whole talk. And you always need independent assessment, and so I have to thank these guys for that. Several others helped out who, because of the potentially controversial nature of the discussion, didn't want their organizations to be attributed. Katie Griffin, my daughter, helped with the PowerPoint styling. I thought just words in a row on black and white were good enough, but I was informed by others that that was not the case. So we needed to do better. And then, Josh, if you would stand up just briefly. Josh Fitzgerald, a professional astrodynamicist, helped us out on some areas where, frankly, it needs a computer and some sophisticated software to do the math. It's not the kind of stuff you can do on the back of an envelope, and or even a very large envelope. And Josh helped out quite a lot with that, and I'll point some spots out as we go through the talk on what those were. So with proper acknowledgement, a lot of this talk is just for documentation. I'm not going to walk you through every slide, and I'm not going to solve the rocket equation for you in real time, and so on. But for those who look at it online or want to pull it up later, I've tried to be complete with many references. So first of all, for those of you who don't do this every day, there is a history of humans to the moon, done before many of you in this audience were born. But it starts with, in May of 1961, with Kennedy's very famous Man-Moon Decade speech, one of the greatest examples. It's taught by me in program management classes, is how to capture what it is that you need to do succinctly. And frankly, I'm not sure that the program would have been concluded successfully had Kennedy's speechwriter not been so astute. So that, from the speech emerged 7 attempts and 6 landings to go to the moon. Cost about $26 billion in then-year dollars, about $260 billion in current dollars. Sounds like a lot unless you start thinking about what we spent in the Mideast to have a much lesser result. Worthy of note is that about 85% of the money was spent creating the capability and only about 15.5% using the capability. That has to be a first for any transportation system ever created. The last 3 Apollo missions were canceled by the Nixon administration, even though all of the hardware had been bought. The residual hardware sits today at Kennedy Space Center, Johnson Space Center, Marshall Space Flight Center in Alabama, where I live. Or some of it was used for some of the 4 Skylab missions, and some of it was just scrapped. The cost references are in the blue at the bottom for those who want to look it up later. A quick chart on how it was done, provided to me by one of the people who was not able to be named. I'm no kind of an artist. But as some will remember and others will see, basically we launched one rocket that carried everything. It was good for, it was big enough to carry 2 crew to the moon for a maximum of 3 days for the later missions, as long as you stayed relatively near to the equator. That was not a limitation of the rocketry, but it was a limitation of the length of time people could stay on the moon, and we'll talk a little bit about that later on, and some pictures to sort of remind people what we did to make it happen. After Apollo, a very long desert for true space exploration. Richard Nixon, then president, said, directed NASA to build a space shuttle. Nobody ever said, where's it going to go? Kind of important for a transportation system. In 1984, Ronald Reagan, who had much to his credit, enormous amount to his credit for this country, directed NASA to build an international space station primarily as a reaction to the then Soviet Union's small space station, which they were using basically as an incentive for other nations to align themselves with them so their astronauts could get a ride to the Soviet space station. I mean, that's just the reality of it. So Reagan directed NASA to build a space station and to do it internationally. But other than that, no one ever said why. What are you going to do with it? And I'm not sure that even today anybody knows what it's really for, what it could have been for, and whether or not we got out of it what we put into it or more. In 1989, on the 20th anniversary of the Apollo 11 landing, the first President Bush said we would return to the moon, this time to stay. In the way that politics goes, 4 years later, that was canceled by the Clinton administration. I was actually in charge of that effort in that era, and it was very difficult. It was my first time being canceled. In 2004, the second President Bush said that we would, and I'm almost directly quoting here on the chart, finish the International Space Station, retire the shuttle, develop a new crew transportation system to replace the shuttle, and then return to the moon. And in 2010, that was canceled by the Obama administration. Following that, in the Trump and successively Biden administrations, we're trying again, and the direction to NASA is to return to the moon. Most of this talk is about how we're going to do it, but more importantly, why it's important. So, starting out 50 years with no consistent theme, as you could see from the history. Well, why was that? Well, the most common criticism of Apollo was that it was unsustainable. But if you look at that in even the slightest detail, it clearly not because of the money. The hardware for Apollos 18 through 20 had already been bought, and there was, the learning curve. We were well down the learning curve. In 1971 and 2, we did 2 lunar missions a year for, in then-year dollars, less than $1 billion a year in a NASA budget that was $3 billion a year at its very lowest point in 1974. So less than a third of the budget, where typically NASA has spent well north of 50% of its budget on human spaceflight. So it's certainly not fiscally unsustainable, it just wasn't sustained. So it's nice to talk about money when you don't really want to say why you want to do something. But the real reason, and this is the point for which my co-author gets the credit, pointing out to me that Apollo was really about tactics, not strategy. Back then, we were trying to establish U.S. leadership in space, which we defined as beating the Soviets to the moon, and they were Soviets then, not Russians. What are we trying to do now? Maintain U.S. leadership in space, beat China to the moon, and I gave you a reference from the current NASA administrator saying exactly that. Well, but that's just like Apollo, except that it's China instead of the USSR. So it's no more strategic, it's as tactical. We wanted to point out that, trivially, that winning a race is not a strategic goal. Even brilliantly executed tactics, and Apollo was brilliantly executed by most normal human standards, have to be linked by a sustainable strategy if they are to be sustained. So Lisa and I will give you a quote from Sun Tzu. Strategy without tactics is the slowest route to victory. Tactics without strategy is the noise before defeat. Said 2,500 years ago. Some things are still true even if we didn't say them. So what's the right strategic goal? If you're going to do this, why does it matter? Well, if you think about it even a little bit, space exploration, spaceflight, is about leading the world into a new human domain. In the same vein as, lots bigger, than opening up North and South America by Europeans. This is an imperative the imperative to expand the human range is an imperative that is as old as the human race, or there would be no humans outside the Great Rift Valley of Africa. The fact that we are here is a consequence of that imperative and of the willingness of our forebears to take the next step to see over the next hill and take the chances in doing so that maybe what awaits you is not good. But maybe what awaits you is good and you're able to build on it, and that's been the human history for 1,000,000 years. Literally 1,000,000 years. This is a goal we should want to pursue whether or not we have an adversary. This is a goal that is self-sustaining. It doesn't go away, and to date in human history, it has always proved in the long run to be valuable. It's hazardous for the individuals who are at the point of the spear, but for the race, it has proved to be valuable. It's not a race. There is no finish line. And it's not a strategic goal for people, in Oscar Wilde's famous phrase, it's not for people who understand the price of everything and the value of nothing. So, as well as we knew, it has been expressed, was expressed by the late Jack Marburger, who was the science advisor under President Bush, the second President Bush, and in a speech that's too little known, and we reference it here, the question about the vision for space exploration boils down to whether we want to incorporate the solar system in our economic sphere or not. An economic sphere matters a lot because in the long run, human beings are not going to continue to pursue an activity that doesn't bring benefits in some form. That's what economics means. So when we talk in our presentation here about the imperative to expand the human range, it's because it has always paid benefits. And that's what Jack is pointing out. Do we or do we not want to incorporate the benefits that come to us from the rest of the solar system in our economic sphere? But this is for people who want to play the long game. You have to begin with the end in mind. You have to ask yourself, in the year 3000 AD, to pick a number, are we going to be using the resources that exist in the rest of the solar system, or are we not? I'm fond of pointing out, as I have in other speeches, that it was 1,000 years from Viking longships to Carnival cruise lines. And I say that as a joke, deliberately to get your attention, but it was 1,000 years from Viking longships to Carnival cruise lines. It takes a while to accomplish great things. But with strategy in mind, with the necessity of linking tactics with strategic goals, it's also important to remember that being first also matters, and it matters a lot. We're not the first people to observe this, but we'll emphasize it here. The standards are set by the people who show up, not by the people who stay home and watch. Communications, navigation, transportation, all of these disciplines carry engineering, political, protocol standards. We ask, why is all international air traffic control conducted in English and not some other language? The rules are made by the people who show up. Who can use what resources, where, and how? That's not set by the people who are watching. The values are those of the people who show up. All the things we take for granted, the rule of law, property rights, individual liberties, self-governance, all of that. Not every society on Earth that is capable of pioneering the space frontier shares those values. President Kennedy, who really had a wonderful speechwriter, is quoted as saying, "We go into space because whatever mankind must undertake, free men must fully share." And that is the nub of it. A couple of other quotes from Kennedy where he points out, and Lisa and I would say, we once understood this without necessarily having to be told all the time, that space exploration is going to go ahead whether we participate or not. And no nation that expects to be the leader of other nations can expect to stay behind. The United States still expects to be the leader among nations. I think we should, but we actually have to put our money where our mouth is. As Kennedy said, the eyes of the world now look into space. We've vowed that we shall not see it governed by a hostile flag of conquest, but by a banner of freedom and peace. And then a little bit later in the same speech, he notes that the vows of this nation can only be fulfilled if we in this nation are first, and therefore we intend to be first. It was a brilliant speech, September of 1962 at Rice University. And the reference is there if you care to look it up. China gets it. This is a quote from Ye, I'll never pronounce this right, but Ye Paijian, the former Director General of the Chinese Lunar Exploration Missions. And Paijian said, "The cosmos is an ocean, the moon is the Diaoyu Islands, Mars is Hunyan Island, Scarborough Shoal. If we can go, but don't go, future generations would condemn us. Once others are there, once others have occupied, no matter how much you wanted to go, you couldn't." And that says two things. First of all, they get it. Second of all, it's about how they think. The United States would never even, it would not cross our minds to say we're going to the moon and we're going to claim it and nobody else can come. But that's what they're thinking. So what are our adversaries doing? And I use the term adversaries because while the United States never declares anyone an adversary, the adversary gets a vote, and China regularly declares us to be their principal adversary. It might be a good idea to pay attention to that. So what are they doing? Well, first of all, China has announced, again, we've provided a reference, a lunar landing by 2030. Maybe they'll make the date, maybe they won't, but that's their goal. And we haven't said where. Maybe near the South Pole, like the Chang'e 6 that just landed a couple of weeks ago at Aitken Basin, and then returned a sample to orbit, and with a little bit of luck and skill on their part, which they have, they'll be returning that sample to the Earth. China and Russia are establishing a lunar mission partnership, footnoted there, and inviting others to join. There's no more classic example of the use of soft power in global power politics. You're doing something everybody wants to be a part of, and all they have to do is line up with you. There are very few partnership options available to other nations that lack independent human space access. The three that can do it are China, Russia, and the United States, pretty soon India. We think, Lisa and I think pretty soon India. Sorry, a rhetorically stupid question. With whom would the United States prefer others to align? Is it in the interest of the United States to allow an environment to be created where nations that are not necessarily aligned with anybody choose to align with China and Russia because this is one of the benefits and there are no penalties? What are we doing? Well, for those who watched it a year and a half ago, we saw the unmanned Artemis 1 vehicle perform a circumlunar mission. It was quite successful. Issues with the heat shield, which you've no doubt read about in the newspaper, but frankly, that's mostly because the United States has forgotten how to build a heat shield. We once knew. We'll figure it out again. I have great confidence that we'll figure out how to do a heat shield. Artemis 2 will be a 2025 repeat of the Artemis 1, but with people. The crew has been named. 2026 is the official landing date for Artemis 3 in the South Pole region. Footnote is to indicate that is quoted as the official date, along with the caveat that it's probably going to slip because there's no way it's going to happen by 26. Artemis 4 will deploy the Lunar Gateway, pictured on the slide to the right. This is basically a space station in lunar orbit with no more clear mission than the space station in Earth orbit, at least for those of us who study these things. And Artemis 5 and beyond, Orion will the Orion spacecraft, which I'll show you in a minute, actually remains in the Lunar Gateway while 4 crew instead of just 2 go to the surface. How are we doing it? To the right is pictured the staging orbit. It's called a halo orbit. We're going to supposedly park the Gateway in that orbit. That orbit is the solution to what's called the circular restricted 3-body problem. It's one of those things that can't be solved even on a really big envelope. It's basically the problem of calculating the motion of a small mass moving under the influence of 2 larger bodies, so a spacecraft in the Earth-Moon system. And oftentimes people will add in the Sun but for the Earth-Moon system, although that is now a 4th body, but because it does have some influence. No less than Isaac Newton once said that the motion of the moon is the only problem that ever made his head hurt. That's a direct quote. I share his pain. So there are a number of halo orbits. NASA has chosen an approximately 33,000 by 70,000 kilometer lunar orbit. It makes 9 passes around the Earth every 2 months, so it's called a 9-2 resonance. And it has every 6.5 days you can access the lunar surface. Now I'm going to talk about that a little bit later on. Note, every 6.5 days you can access the lunar surface. Who does what? NASA defines the architecture, procures the launch system, procures the Orion command module from Lockheed Martin, provides the crew return, provides from the Gateway to the Earth's surface, procures the Gateway, the Orion, the SLS, the human landing, procures the human landing system, procures the spacesuits. The acquisition strategy is largely a so-called commercial service model, where NASA buys a mission execution but not the hardware. I will tell you frankly that many of us, certainly including Lisa and myself, are appalled at the idea of labeling something commercial for which there's no business plan that can ever, not ever, but in the foreseeable future, no business plan that can return value to an investor. So this is really something that should be paid for by the taxpayer if done at all. Contractors are responsible, I'm not going to run through all those things, for basically designing and executing the human landing system portion of the mission in response to NASA's architecture. SpaceX has been given a total of $4.3 billion for a firm fixed price, $3.6 billion awarded so far, and Blue Origin has been awarded $3.2 billion to do these. Compare those with the per mission costs from the Apollo era, and you can see that we've signed up for a situation where we're hiring private contractors as a nation to execute missions on our behalf with the assumption that they will build the infrastructure to do the missions. This is for you to take home and look at later. It's a great chart. It's a NASA chart showing the different ways to get to the moon and how much delta V is required to do it. In space systems engineering parlance, delta V is the velocity change that you have to put a spacecraft through to get it to go where you want and do what you want. And it's more precious than gold, and that's not a joke. It costs more per pound than gold by a lot. I would, if you carry out one thing from this chart, it's that going through the halo orbit that NASA is doing costs you 600 meters per second of extra delta V, and we're going to see the consequences of that later. For those who want to study it later, this is the picturing of the classical orbital elements. This is one of the charts that Josh furnished for me that I mentioned I would call out later. The chart on the left is how you would see things if you're sitting at your spot on the moon where you've landed and watching your return orbit drift away from you as the moon rotates. You're sitting on the moon. You don't know that it's rotating, so it looks like the orbit that you came in blue and that you depart on in yellow, it looks like those are drifting around on you. The importance of this is that only every couple of weeks is it possible to return to Earth from a given spot on the moon. And I'm being very loose with my language here because I don't want to get too deeply into it. On the right is the chart for how things look if you are taking the God's eye view in inertial space, because in inertial space the orbits are fixed up to minor perturbations that don't concern us here, and so the moon rotates under the orbit. And if you look at the little red dots, that's how much it would rotate in several days of time. The moon rotates very slowly, obviously once in every 27.3 days. Again, the challenge is arriving when you want, such that you can leave when you want. So we talk about wanting to go to the moon, and land at a pole. So let's talk about polar parking orbits. So access to a polar site is pretty much any time from Earth. There are no, if you looked at the other chart closely, no right ascension of ascending node requirements. You don't really have to worry about what time you arrive. If you're trying to land near a pole, you can arrive pretty much any time. If you are landing near a pole and in a polar parking orbit, you can abort to the mothership anytime, a couple of hours. Fast transfer back to Earth from a polar site is possible about every 2 weeks, as I said a moment ago. Some flexibility depending on your available delta V margin. And you might need to choose, if you want to come home, you might need to choose between staying longer on the surface or loitering in orbit. But those are choices you can make. Global access to any non-specific polar site is available for you about every 2 weeks from a polar parking orbit, with again some margin for when you depart from Earth, how long you decide to let the trip take. You have choices there, and how long you're willing to loiter in lunar orbit. So you have some flexibility. You can get to anywhere you want. You can get to anywhere that you want pretty much any time you decide to go, but you can't necessarily come home anytime you want. And those things are important to know. Okay. Now, quickly, the SpaceX design, and this is a feature I would want you to note. About 20 tanker flights is required to fuel up one orbital landing, one lunar landing, sorry. So another thing that I would want you to note from this chart, the NASA specification requires the lander to be able to loiter for up to 90 days to wait for the crew to arrive. That's going to be significant. This is what the SpaceX lander looks like. I won't run through the sequence of operations. A lot of people are concerned about the difficulty of stabilizing a lander that looks like that, especially given that 2 of the last 3 landing attempts by any nation have, one by Japan, one by the United States, one by China. Only the Chinese one stayed upright. For later reference, this is what Artemis 3 looks like. This is a NASA chart. So here's the SpaceX concept of operations. As I said verbally a moment ago, possibly as many as certainly 15 to 20 refueling flights required to execute one lunar mission. Blue Origin is the other contractor who has been paid to do this, won the right to do it in a competition. I'll let you read that at your leisure. I don't need to be reading any more word charts to you. Very similar, and probably a picture says more than anything else could do. Down here, we don't really know how many refueling flights are required because Blue Origin hasn't said. They do. I think my personal opinion here it's a little bit better approach to do the refueling, the last refueling in lunar orbit, rather than spending several extra days hauling fuel around, which can evaporate, and we're going to talk about that in a little bit. But basically, you go to they go to near rectilinear lunar or halo orbit, transfer down to a low lunar orbit, land, come back up, come back to Earth. Now, even a casual reading of those charts says that the present mission designs are very complex. Complexity equates to risk, loss of mission, loss of crew. Loss of mission occurs when you spend a bunch of money and you couldn't get to the end of what you were trying to do. Loss of crew is, of course, much more serious. Something goes badly wrong and they just don't come back. Now, when you look at the mission designs that are crafted to fit the architecture that NASA has specified, almost the first thing that occurs to you is this line right here. To put 4 people on the moon ought not to require significantly more total mass and complexity than 2 Apollo launches of 2 people each. Just on first principles. Otherwise, what are you getting that you wouldn't get if you just magically go back and rebuild the hardware and send 2 Apollo missions? You get 4 people on the moon for several days. So what are you getting with all this complexity that you don't otherwise get? And the answer is, frankly, not much. There are some slight differences. The lunar poles are a bit more difficult to reach than the equatorial regions, although frankly not significantly so. And 4 people for a week is more difficult than 4 people for 3 days. But in the magenta, it just shouldn't be as difficult as the architectures that are presented imply. The Artemis mission designs impose a very high crew risk. Abort from the lunar surface can require up to 3.6, roughly 3.5 days to reach the safety of the mothership, which is parked in near rectilinear halo orbit. The optimal return, where you require only half a day to get back, is only available on 6.5-day centers. So imagine if something goes wrong and you really need to come home. Well, you can do it fairly quickly every 6.5 days. Otherwise, not so much. You're going to be stranded for 3.5 days. Now, you might be stranded in orbit. You can imagine a situation where you've had a fuel leak or fuel is boiling off more rapidly than you expected, and you kind of have to use it or lose it. So you get off the surface and into near rectilinear halo orbit, but now you might have to wait as much as 3.5 days to get back to the mothership. And by the way, Orion has no capability to leave halo orbit and rescue the crew in low lunar orbit. During Apollo, the command and service module could always come down and rescue the lunar module if it could get into any kind of orbit at all. That's a significant difference. I will say straight up, I said it in front of Congress, if I were still the administrator, this is not a risk of crew for early missions that I would be willing to sign up to. Once we've been back to the moon for a lengthy period of time and have a lot of infrastructure there, now you have a different story. You can always, as to use the Antarctica example, you can winter over in Antarctica. You're not going to winter over on the moon, but you get my point. But the first few times back, when you don't have that kind of support infrastructure, I think risking crew is something that the United States just shouldn't do. Now, this chart is nothing but basic statistics. If you have a whole bunch of operations that have to work right in sequence, and each one is an independent event, let's assume, as in the example for the SpaceX's and Blue Origin architectures, let's assume you have 50 operations that you would have to do. Each operation being a launch, a docking, a fuel transfer, undocking and disposal. And let's assume that you have a 98% reliability meaning only one of those missions is going to fail in 50 tries, you have a 74% chance of completing your mission. So you've spent a ton of money. It's a national imperative, and 1 out of 4 times it fails if you only have one failure in 50 tries. That's a high hill to climb. I have had people tell me that, oh, well, if a problem occurs, we'll just launch another tanker. Seriously? You launch a tanker, it went wrong. This is using the same components that you're going to use to launch Crew. Are you really just going to launch another tanker cavalierly with a system problem that might be affecting Crew? I wouldn't. Almost never mentioned is the issue of propellant boil-off. All of the architectures so far proposed use cryogenic propellants: liquid oxygen, liquid hydrogen, liquid methane. So, from flight experience, for a Centaur 3, which is the only current cryogenic upper stage that the United States has, it's been flying for over 60 years, slightly modified, but essentially the same vehicle. Experience is that you lose about 2.5% of your propellant per day for LOX and about 15% per day for liquid hydrogen. Now, with a little bit of insulation, something pretty feasible, you can cut that down to about 1.5% a day and 5% a day. Doing better is truly critical for long-duration human space exploration. This is a critical technology for the future. Learning how to keep cryogenic propellants cold for long periods of time and be able to count on it. You don't want to be on the moon or at Mars trying to come home and you don't have any fuel left. So it's critical. But for to have the first human lunar missions in 60 years, depending upon the development of that technology, seems chancy. Maybe not. Maybe we don't want to do that. Now, the Blue Origin team cites that they're going to use solar-powered refrigeration for cryogenic propellant conditioning. When we can realize that, it will be a huge benefit. It will cut losses down to maybe 0.1% per day. But nobody knows how to do that at present. And it takes an awful lot of solar power to cool cryogenic propellants to the point where they don't boil off. I've given you some technical references at the bottom there. But let's look at some numbers. What these numbers on the chart say, that even 5 days on the moon with a cryogenic lander, methane or hydrogen, which is what is being proposed, with present technology would be very challenging. Spending 5 days on the moon with reasonable insulation, you're going to have 93% of your LOX and 90% of your hydrogen coming home. If you were to spend 30 days, counting the orbit time, you're down to 64% and 22%. That's not workable. And the 90-day loiter that NASA has specified leaves you with 1% and 26% of your fuel. 90-day loiter is a government specification. The contractors have to be able to show that they can do that or the mission doesn't work. So the chart speaks for itself, but 90 days is practically unworkable. A month is a huge problem, and 5 days is tough. I talked earlier about the amount of extra delta V that's required. So what's necessary to understand is that all of these architectures, and I think correctly on this point, end up staging out of a 100-kilometer circular low lunar orbit. Now, from that orbit, because we have actual flight experience, and this is another one of those calculations you don't do on the back of an envelope, it's about a delta V of about 4 kilometers per second with margin, about a little bit over 2 kilometers down, kilometers per second down, and a little less than 2 kilometers per second up. And it depends on the details of the trajectory design and things like thrust-to-weight ratio and a bunch of stuff you don't care about, but it's about that number. That's independent of how the lander is delivered to the parking orbit, whether you go through halo orbit or whatever, however you get there. Once you're in that parking orbit, that's what you have to do. That's hard. Okay, so 4 kilometers per second in a crew vehicle is hard. The lander is at the very end of what we in the business call the Delta V gear train. It's a succession of maneuvers that you have to do. Any additional requirements on the lander should really have anything above what it absolutely has to do should really earn its way aboard, or it shouldn't be done. Fundamental principle of system engineering. Don't make the hard job harder. There is a penalty, a total of about 750 meters per second, Delta V required to get from halo orbit down to low lunar orbit, and about the same on return. The net, when you're all done with it, you make up a little somewhere else. It's about 600 meters per second extra for the whole mission. But for the lander, you're imposing an extra 1.5 kilometers per second of Delta V down and up on the lander. It's really preferable from a system engineering point of view to take that penalty somewhere else in the system, not on the hardest thing to build. That's the message of that slide. So the Artemis architecture imposes penalties without benefits. You have a nominal 1-month mission ranging from like 26 to 32 or 33 days, just depending. And it's about double that of a more direct approach. So the more time you expose crew to space, the riskier it is, the more radiation they have. Oh, by the way, the present version of the Orion crew module has a 21-day active operations lifetime. So the nominal mission exceeds the spec lifetime of the crew vehicle that's supposed to take them there. That obviously is a limitation that needs to be fixed for the future no matter what, but that's where we are right now. The longer flight time increases the required mass of consumables, higher radiation exposure, and it gives you additional time for things to fail. Most of the system is one failure tolerant, meaning that there are a whole bunch of things that can fail that mean you have to come home right now. Because after the first failure, now you're 0 failure tolerant. That's a problem. So staging through NRHO, halo orbit, is a system problem. What Lisa and I observed on this is that when you're staging through NRHO, you're prioritizing the Orion Delta V capability as the limiting constraint. And it is limiting. The Orion spec Delta V is 1.25 kilometers per second. It's enough to get you into low orbit or out of low orbit, but not both. The net on this slide is that the Artemis architecture is shaped around using the lander to solve an Orion problem. That's what you're fundamentally doing. You're imposing requirements on the more difficult part of the system to build in order to save the less difficult part of the system to build. Not a good system engineering practice. And as we're going to point out in the next few slides, there are easier ways to solve the problem. So what we're proposing here is a 2-launch scenario. Uses the government built, and the first version of which has already flown, Space Launch System. Actually, we don't care what you launch it on. If Elon had Starship working by the time we were ready to go, happy to buy a ride on Starship, don't care. So you first launch the uncrewed, fully fueled, storable propellant lander with less performance, but it doesn't care how long it has to stay in lunar orbit. You can leave it there for a year. And you use a lunar orbit insertion stage, basically that partially fueled Centaur 3 that I mentioned earlier, about to go out of production, but still in production, 18 more of them still being flown. And I checked with United Launch Alliance, which builds it, and they're happy. I'm sure you're shocked. They're happy to build more for money. The Lunar orbit insertion stage injects the lander into lunar orbit to wait for the crew. Note here, you don't have any cryo storage limit, and you can keep it in lunar orbit for a year with an expenditure of about 100 meters per second of delta V. I gave you a reference on that. Then when you're ready, you launch the crew. They rendezvous in lunar orbit. They descend and land and come back up. There's no fixed mission duration. You don't have to wait. You don't have to time things on 6.5 days. If you need to come back sooner or stay a little longer, you can do that. You can get back to Orion any time from the surface for a near polar mission. And if you choose to go to an equatorial site early on, you can come back to Earth anytime. The mission elapsed time is, if you want to use a polar landing site, then you have to time things in a way that respects the fact that you can only get back to Earth about every 2 weeks. That's not particular to the architecture. God's in charge of that one. That's a joke. It's the way that the universe is designed, with orbital mechanics being what it is. With the Earth and Moon are where they are, you can come home about every 2 weeks. Mid-latitude surface stays are constrained by both the Orion rendezvous and Earth return options. So the mid-latitudes are the hardest places to go to. Equator's the easiest, poles are next, and mid-latitudes are really hard. So this is what that looks like. Notice that you don't have 10 or 15 or 20 refueling flights. So you have 2 launches for a 7-day surface stay. This is some stuff that says how you'd think about things. You'd always deploy the lander first, because if the lander doesn't make it there, there's no point in launching crew. There's an interesting question that, going through the math on all this, you have to ask yourself, is it wise for the lunar lander to use the lunar orbit insertion stage, or just make the lander tanks bigger? For storable propellants, it turns out that it's probably a good idea to make it separate, and when we get to the point where we can make cryogenic propellants stay cryogenic, then you could change. Then it would be worthwhile to do it, but not yet. I'm not going to run you through this. This is for later looking at it. Basically what this says is that it's a doable thing with current existing systems. We even took a look at more subtle things like how much prop does boil off in 3 days, and the fact that real rocket engines don't use, if you're burning liquid oxygen and liquid hydrogen, what's called the stoichiometric ratio is 8:1. If you burn it exactly the way that the chemistry wants to work. But if you do that, you'll also burn up your engine. So real rocket engines they cool the engine with fuel. So we took that into account. It all comes out to be very easy, very doable, lots of margin, which is to the point of all that math on the last couple charts, is this to get down to this point here. You have 32 metric tons available to build a lander that can carry 4 people instead of 2. And the last time we did this, we built a lander that could carry 2 people for 16 metric tons, exactly half of that. So it is a relatively straightforward engineering problem to build any kind of a vehicle designed to hold 2 people, to build one to hold 4 people for twice the mass of what will hold 2. Because there are an awful lot of overhead things that, don't change with the number of people involved. So that's doable. This slide says that you can do the same thing for the Orion crew module. You can use the lunar orbit stage, lunar orbit insertion stage that puts the lander in orbit. You can also do it for the crew module. An interesting question, which I've been asked on a number of occasions, is why don't you just make the Orion tanks bigger? Well, you can. You can, and you can fit it barely on the bigger version of the SLS, and you have to make the fuel tanks bigger, not terribly much bigger, but you do. But it's not a really practical early approach because you're maxing out the capability of a launch vehicle that you'd rather not do. And being entirely practical about it, if you have to re-navigate the NASA, European Space Agency, Lockheed Martin, and Airbus acquisition maze, that will probably end up being, without any intent to be cynical, that will probably end up being the pacing item. So for early missions, I think what we would recommend is just use the same lunar orbit insertion stage that you do for the lander. This is the chart that says you can actually make it home. This is another area where Josh Fitzgerald helped out a lot, because this is a calculation that you to compute the departure velocity versus trip time in the Earth, Moon, Sun system is another one of those problems that doesn't fit on the back of an envelope. You need specialized software to do it. But it turns out that if you're, say, let's pick a nominal 3.75 day trip time home, the departure velocity out of low lunar orbit from this chart is about 0.85 kilometers per second, well within the Orion spec delta V, which you haven't used because you're parked in lunar orbit. You got delivered there with full tanks, and they're not evaporating. And in fact, you even should have enough residual delta V to cut your loiter time if you needed to come home early or wanted to stay a little late. For about 225 meters per second per day, you can shave a day or two off or add a day or two on to what you're trying to do. I'm coming up on my hour of time that I was asked to talk. So summary. There exists at least one conservatively designed, lower risk, two-launch human lunar mission architecture satisfying NASA's basic requirements, which are 4 crew, global access, 1 week, 21-day Orion design lifetime limit. It closes with ample margin, doing it the way we're talking about, and even with the very worst case that you could ever have of a 1,350 meter per second insertion delta V, it'll still close. Not with much margin, but it'll close. We do point out that it might be better not to start with the hardest problem first. Save the harder problems for later. You get anytime crew return, nominal or abort, from the lunar surface to Orion, and or from equatorial or polar sites, and you can return to Earth anytime from an equatorial site. Many fewer, much less complex operations, and no new technology. You have to build some stuff, but you don't have to develop anything new. Final thoughts, in all humility, this is a straw man design. There are many options that occurred even to us by which you might improve it while you're doing. This is very straightforward, but an interesting question is everybody uses a 100-kilometer low lunar orbit because that's what we did before, and it's fine. But what's the best parking orbit? If you were to try to balance requirements between the lander and the lunar orbit insertion, what's the best parking orbit? I don't know. It's something that would be interesting to look at. Other staging orbits that aren't circular exist. Josh pointed out to me that there's a 12-hour, 100-kilometer by 3,000-kilometer orbit that gives you 2 options a day to get home, that the Orion can do all by itself. Another interesting question, if you're looking for excursions, is you have a lunar orbit insertion stage. What's the best way to use it? We're only filling it halfway full in our approach. Suppose you filled it up. How would you trade off the launch mass requirements versus what the stage could do for you? We don't know. We do know that the conservative design option that we presented is almost certainly not the best one. How soon could you get there? Depends on what the priority is. And the priority is not what politicians say is the priority. The budget is the priority. What you elect to spend your money on and what you decide you're not going to spend it on is the real priority. The lander ought to be the pacing item. In Apollo, the lander contract was awarded in November of '62, and the first uncrewed flight was made in January '68, 5 years, 2 months later. If we couldn't do better than that today, I would kind of say shame on us, and maybe the Chinese deserve to win. But that's not a good thought. That's me being sarcastic. But that's, I think, kind of the pacing item. So if we were serious about it, we could do it right around by 2030 or so. Couple of questions, maybe rhetorical, maybe not. We don't have a very hardware-rich program as it's currently planned. There's no crew shakedown of Orion in low Earth orbit. The program seems somewhat hardware poor to me. Of course, I admit I'm a suspenders and belt kind of engineer, but it seems kind of hardware poor. The other question that really jumps out at you, again, the lunar poles are harder to land at than the equator. Is it a good idea to go to a lunar pole the first time back in 60 years? There's poor lighting on the approach, and you always want the pilots to have the ability to take over manually if needed. It was needed on earlier missions, and you can expect that you're definitely landing on more difficult terrain than we did before, with unknown surface characteristics and more restricted Earth return opportunities. So as the joke goes, other than that, Mrs. Lincoln, how'd you like to play? It's a really good question that we should be asking ourselves is, do we want to start out with a really hard problem for the first time back to the moon in 60 years? There are a lot of other interesting sites, and we don't understand how starting with the hard problem first advances either the tactical goals of returning to the moon ahead of China or the long-term strategic goals of opening up the solar system to the human economic sphere of influence. So with that, that's the hour you asked me to fill, and I'm done. Plenty of charts to look at. Lots of math in the charts for those who want to go through it. It can be quite interesting.
So we have time for questions. I'm going to start with a question.
Yes, sir.
So you kind of skewered the strategic goal being just to get to the moon before someone else again. What is the strategic goal?
Well, as we said on the chart, the strategic goal is to expand the human range of action.
That's a
as
very
we have
broad
done
goal.
for 1 million years. And the
No,
next place to expand it is the solar system, and the United States should be taking the lead to do that.
So you'd say this program should be something other than just getting to the moon, landing there, and coming back.
That's right.
It's got to be a piece and a plan to move out into the solar system as a whole.
That's exactly right. That
Okay.
will bring benefits to the human race, we think. Now, if it turns out that it doesn't bring benefits to the human race, we should stop. But we believe that, again, with the idea that it was 1,000 years from Viking longships to Carnival cruise lines, maybe we should think long term, and this is the first step in a strategic outreach.
I have one more question, then I'll go to the audience.
Sure.
Why the focus on 4? Why not 2 to start?
Well, they are starting with 2. The first landing will be 2 people. They're designing the capability for 4, and I think that's a good idea.
Okay. Red microphone. Stand up,
Okay.
tell us your name and if you're a member.
Colin Elbertson, I am a member. I want to thank you. That was a bracing, if a little bit depressing talk that you gave, but that's what we need sometimes. I was really struck by what you were talking about when you were reminding us of actually just how sustainable Apollo Saturn actually was in its time. And I'm just wondering, because I've never gotten a really good answer to this. Given the sunk cost into SLS, it's a purely academic question, but I know they say that the tacit knowledge of machining and tolerances and engineering are long gone. The engineers and mechanics are all dead. But we have the blueprints, we have the static models that we could reverse engineer. Did anybody ever think about maybe reopening the Saturn line and just like going back to what worked? And along those lines, couldn't we do the same with Apollo hardware in some ways too?
Well, of course you could, and I've thought about that. And when I worked for Lieutenant General Abramson back in the Strategic Defense Initiative under President Reagan, Abe had me do a study on whether or not it would be possible to resurrect the Saturn line. It was possible. It would be possible today, but we can do better. We can do better.
Can we though? I mean, the thing is that you talk about the launch. I mean,
I'm not going to change my story. We can do better.
The tons to orbit. But I mean, even when you're looking at something like Starship Super Heavy, originally it was planned to have like a total weight to orbit that was going to be in the Saturn V territory, but because of the additional weight that they've had to do in the interstaging, they're now only able to get you like maybe 50, 60 tons into orbit. So again, why not go with what worked in the past? Maybe we can't do any better. Is my question.
Okay, we just might have to have a difference of opinion. I think that we can do better. We have to decide that we're going to do it. It certainly would be an option to go back and rebuild a copy of Saturn V and fly it. That would be an option. We have a space launch system. It doesn't have to cost what it is being allowed to cost, and it works fine. We get locked up on the first 100 miles. That's not the interesting part. If SpaceX gets Starship working at a sufficiently good level of performance, or if Blue Origin gets New Glenn or a successor vehicle working, to be honest, as a space systems engineer, the only thing I ever knew anything about, I'd be happy to buy a ride from them. Who cares? It's not about the first 100 miles. It's about what you do after that.
Blue microphone somewhere?
Hello, Matt Kaywood, member, but not an aerospace engineer. Why is the SpaceX plan have so many fuel runs? And I didn't quite understand that part of the mission. It seems like an awful lot. Is that just a limitation of the vehicle? And what is their plan for dealing with the risks of that they can't get that 100% probability under any circumstances?
Well, it needs a lot of launches to do it the way it is being done by either SpaceX or Blue, because they have so much delta V penalty imposed on the thing which is going to do the landing. So you have to have a lot of fuel. And if you're transporting it up from Earth, and I don't know no one knows the current payload of Starship or New Glenn, you're bringing it up in multi-tens of tons chunks, and you need hundreds of metric tons, and it's boiling off while you're filling the tanks. You have a serious question there of whether you can actually ever fill the tanks, because it might boil off faster than you can fill it. So it needs a lot of flights. It's not real. That part's not rocket science. It just needs a lot of flights.
We'll go back to the red microphone.
David Herman's member. Mike and Lisa, first, thank you for putting this together. I appreciate it. Had a question about the kind of end stages of your topic. Talked a little bit about utilization of the moon as a next step for the human race and for the economics. Didn't hear much on the addressing of what's next for either the current NASA Artemis missions or your proposed alternatives. How do we establish a permanent human presence using your alternative, and why is that better than the current NASA plan?
Well, the mission architecture that we proposed here is, sorry, I hate to be trivial, it's better because it uses a lot fewer launches, has a lot higher probability of success, poses a lot less crew risk, gives you many more options to, bail out if something goes wrong. Those are the features that it offers. We're not even saying you couldn't do better.
Sure.
We're just saying, the current approach is risky for crew, takes a long time to execute any given mission, has a very high probability of something going wrong, and you may not have killed anybody, but you wasted the mission. A comparison of the two approaches just seems straightforward. The next step after the moon, I think the moon would probably profitably occupy us for a while. Before you go to Mars, you really need to learn how to live and work in space. And we've not done that yet, my opinion.
Blue microphone.
Richard Rice, not a member. So let's say the worst did happen. The Artemis mission turns into the Artemis incident and we're delayed significantly. Would the current plans for the commercial space stations be able to alleviate many of the concerns or the causes of the problems?
No. Space stations in low Earth orbit just don't have very much to do with putting humans on the moon.
Red microphone.
You're defining...
Name and if you're a member.
Yeah, James Cohen, I'm a member. You're defining primacy in space as humans being there, but in fact, we're really far ahead of the Chinese or the Russians or anyone else in terms of actually going far beyond the moon. I mean, the Japanese have sent Hayabusa out and have returned material from an asteroid or a planetoid, I should say. We have done the same. We've gone to Mars. We have we have the Mars rovers.
Question?
We're far ahead of anyone else. So why do you think that we need humans to be in these places? We've got intelligent machines, autonomous vehicles that can do a lot more than humans. And is it really cost effective to go risking human lives and the capital that's needed to sustain human life in space? Is it really
I'd have been
worth
happy
it?
to offer my time to you to do the speech.
Yes. All right. So that is my question.
Thanks. It depends on what you're trying to do. Okay, the thesis offered here is that expanding the range of human action is as noble a goal as scientific discovery. Please.
Let's not have a dialogue. You've asked your question.
I'll give you my opinion, and you can flush it on the way out. That's fine. There are more than one thing that is important. We do have an excellent space science program. I often say I worked on Hubble as a younger engineer, and I'm proud of having done so. But scientific discovery is an important goal. Expanding the human range is an important goal. They are not the same. In terms of global power politics, where I've spent a lot of my life, nobody cares. Nobody cares about, other than for a passing note of, gee, isn't that interesting? We landed a rover on Mars. Nobody cares. What they care about is the human adventure. And either that's understood or it's not understood. I'll quote Norm Augustine, who famously said, I'm almost exactly quoting, Norm said, I can't explain the difference, but there is a difference between Tenzing and Hillary climbing Mount Everest and landing an instrumented package on the top of Mount Everest. There is a difference. It's not my quote. It's not my quote, but I believe it to be true.
Let's
Next question.
take a couple of questions from the web, maybe, from our chat, live stream audience.
We have lots of questions from the web, and all over the world, actually. We have some viewers from Sweden and Australia. The first question, Ravi Sharma. He received the Apollo Achievement Award in 1969 and worked on Apollo 8 through 17. The question is whether direct use of Starship is one of the options, or will it only be used as part of Artemis lander like Apollo LEM only?
I have no idea. I'm not in charge. As I've said, I would buy space launch from anybody who can furnish it, but I don't have a more sensible answer than that. I know that the SLS can furnish it, which is why that was what we put in our architecture. If someone else can furnish space launch equivalent to that, happy to buy it. It's like, one more time, it's not about the first 100 miles.
There's another question from Michael Douglas, not a member. Since the Boeing SLS is linchpin of his idea for landing on the moon, should the SLS be scrapped and let a new company try for the contract since the Boeing SLS is so costly?
No.
Okay. We have a question from Kirby Runyon, who is a fellow Johns Hopkins University alum and also a member of PSW. Kirby asks, what are the cultural problems that NASA needs to fix to allow for more common sense engineering for returning humans to the moon?
The cultural problem is not alone with NASA. It can be seen across the US government, where government acquisition, procurement, system engineering is in evidence. The Ford Carrier was years late. The Boeing KC-46 tanker still doesn't work properly. I could go on and on. You don't want my list. The cultural problem that needs to be fixed starts at the very top of the nation.
Another question from the web. Shravan Rao from Melbourne, Australia asks, are there clear scientific goals on top of strategic goals to go back to the moon this or next decade?
I'm sorry, I didn't understand the question.
Are there clear scientific goals on top of the strategic goals to go back to the moon in this or in the next decade?
Yes, I'm completely sure that if you tell any group of planetary scientists or astronomers or other scientists, we are going to have the capability by such and such a date to put X tons on the moon. What do you want to do with those tons for your scientific, to assuage your scientific interests? I'm completely sure that they will find such. I'm not a scientist. I'm an engineer, so I'm not gonna presume to know what constitutes good science or what doesn't.
There's another question from Eric, who's streaming from Sweden. Would you prefer Elon to build an expendable second stage for Starship to simplify its design to launch a more conventional lander in a shorter amount of time?
I don't care what Elon does. I care what the United States of America decides to do and directs to be done. Contractors taking government money are hired hands. We hope they do their work well. But if I'm going to have a custom home built, I'm not going to ask the contractor what kind of a home he thinks I ought to have.
Okay, and one more question from the web. Simon Klott, who is a member, do you have anything to add about the Chinese endeavors? I assume this is referring to going to the moon.
No, I have nothing to add about Chinese endeavors. They seem to be doing a very nice job with their unmanned landers.
Thank you.
Okay, let's go to the red microphone.
Hi, my name is Holly Chick. I'm a reporter with the South China Morning Post, not a member. Thank you for the great lecture. I'm wondering if you could share your insights on the role of the private sector in space station development in the US, and how does that compare to the state-led approach in China? How does that affect the progress of having astronauts in a new space station after the ISS retires? Thank you.
I'm sorry, I don't understand the point of the question.
I'm asking about the role of private sector in space station development. So there is a company trying to build a commercial space station in the US. Yep.
I wish them luck. I'm sorry, I'm not trying to be sarcastic. People who have private money and want to build space stations, I hope they succeed. That's comparing commercial efforts even if they are successful, or private efforts, even if they are successful, it's like comparing the Wagner Group to the U.S. Marines. Okay, it's like comparing mercenary armies and soldiers to the people who risk their lives on behalf of our nation to project power. I wish the commercial operators all good luck, but that's not a national initiative of the United States of America.
We'll take a couple more questions. The blue microphone.
Hello, thank you for this excellent presentation. I'm Kristen Ferry, and I am a member. And my career has wandered in and out of space efforts. And one of the things, these people at NASA designing their mission, they're not stupid people, but they're designing a set of requirements. Those requirements come from stakeholders. You've hinted at some of the stakeholders here. You're very focused on the technical, but there's often other things. An example I can think of in the 1980s on space station, on one of the proposal efforts that I was involved in, we had a map on the wall with congressional districts and pins, for instance, to get votes, make sure we had work in each congressional district. You've hinted at some of this. Can you speak a little more frankly about these non-technical or other kinds of stakeholders that are driving NASA to this much more complex mission?
No, I really can't.
I think we'll take one more question. A red microphone somewhere.
What can you tell us on how things stand from what you showed us?
This is a hypothetical discussion. Nothing going on at NASA reflects anything I talked about here tonight. The point that we're trying to make is that the present NASA architecture is unlikely in the extreme to work. And it is important that we have a workable architecture for the reasons we stated. And so it would be nice to see a workable architecture be put into play.
We'll let AJ have the last question.
Yeah, hi. Hi, my name is AJ. I'm a member, PSW. I guess you have kind of hinted at this, but have you, would you, for the first 100 miles, you said that you are open to various different possibilities. So Falcon Heavy, would that be one of the...
It's insufficient. Falcon Heavy is insufficient.
2 flights of Falcon Heavy.
Yeah, but you can't...
And docking in orbit in LEO, and then increasing the propellant fraction enough to be able to go to the moon.
You can't split the payloads up in a way that allows it to... This is one of those cases, the old joke is 9 women can't have a baby in 1 month. You can't split the lander and LOI, lunar orbit insertion stage.
You don't,
and the crew
you don't
vehicle.
actually have to, but you can put 2 of these things docked together and just increase the propellant fraction of the two
I've
things
not been
together.
able to see a way to do that. I understand the question. I've not been able to see a way to do it. Maybe someone else can see a way to do it.
But I must say that this particular idea that you have is just really nice and very good, and I really hope that of the second half of the first, well, let's say 380,000 kilometer part
AJ.
is very
Okay.
very good.
Very good.
So
Thank you.
Thanks.
Well, thank you very much. You've left us all with a lot to think about. Before you go, we have a few small tokens of thanks for you, a signed copy of the announcement of your talk, signed by all the members of the General Committee on behalf of all of the members, a ribbon. This is our society ribbon. 3 bars on the side are evocative of the symbol for inductance, which was studied by Joseph Henry, who is the first president and founder, and a copy of Volume 1 of the Bulletin of the Philosophical Society of Washington, which explains why they founded the society, who the founders were, and actually has a very nice exposition on what discourse should be like in a scientific society. And with that, we have a few closing remarks before we go, but thank you so much, Mike.
Thanks very much.
Excellent. The 2,499th meeting will be the last of the 20 lectures of the 2023-2024 lecture series, and will close the spring semester on June 28th. And the speaker will be Ben Schneiderman, and he will be speaking on human-centered AI, ensuring human control while increasing automation. Moving into the fall, the 2,500th meeting. That's right, 2,500 meetings. Can you believe it? I have not been president for all of them. We'll be on 6th September, and we're planning a gala event to celebrate. The speaker will be Mark Rothenberg, formerly the chief archivist of the Smithsonian Institution's Joseph Henry Archives. As mentioned before, Joseph Henry was the first secretary of the Smithsonian and also was the first president and one of the founders of the Philosophical Society of Washington, which we today fondly know as PSW or PSW Science. Mark will be speaking about Joseph Henry, the early days of the society, and the importance of PSW and similar scientific societies to science then and now. There will be Prosecco and cake for those of you who attend the reception and dinner for members. The 2,501st meeting is going to be on September 20th, and we do not have that scheduled, the speaker scheduled yet. 2,502nd will be on October 4th. The speaker will be Mark Okrand. He is a creator of languages, including Klingon, in which he's written an opera, believe it or not. He will be speaking, nobody understands it, by the way, but he will be speaking about language in general and the creation of languages, essentially de novo, their popularity and evolution in use. The 2,503rd meeting will be on October 18th. The speaker will be Alexandra Gade, professor of physics and scientific director of the Facility for Rare Isotope Beams in the Department of Physics and Astronomy at Michigan State. Her office is in the cyclotron building, and she will be speaking about the facility, the structures of nuclei, magic number violation, and related subjects. We'll post further commitments to the website as soon as they are set, so please check www.pswscience.org frequently for updates to the schedule. Let's thank tonight's volunteers who manned the cameras and did the Before I adjourn the meeting, I have one last request. You know these little badges that we make you wear? And would you please put them in the little box at the back before you leave so you could save us a couple of bucks? Really appreciate it. Thank you. And with that, I will accept a motion to adjourn the 2,498th meeting to the social hour. A second. All members in favor? All members opposed? Meeting is adjourned.